We'll now more formally introduce the assumptions that we need for difference and differences, and give the proof to show that difference and differences works, that we can identify the causal effect, the ATT, the average treatment effect on the treated. First, we'll just extend the consistency assumption to the setting where there's time. So now we have some time tau that shows up in the subscript for the outcome. And this consistency assumption just says that if treatment, big T, is little t, if it takes on the specific value little t in the data, then the observed value of outcome, y sub tau, is equal to the potential outcome that we would have observed at time tau if we'd gotten treatment little t. So this is just consistency where we've added in this tau subscript here and then said that this holds for all times tau. So here are some examples. If we have the causal estimand, the average potential outcome under treatment at time tau, given that we're in the treatment group, then because we're in that treatment group, t equals 1, we're conditioning on t equals 1, we actually observe that potential outcome under treatment. And that means that we can identify this causal estimand as this statistical estimand here, where we've just removed the potential outcome. So just as before, we have causal estimands when we have potential outcomes, and statistical estimands, these are things that we can estimate from the observational data when we don't have any potential outcomes. So here that's just the parentheses here. The subscript tau isn't important for whether it's a potential outcome or not, right? Because we observe data at every time step. And then it's the same for the control group. If you're interested in the other potential outcome under no treatment, given that you're in the control group, then you can identify this causal estimand as the statistical estimand, where you just have the observed outcome at time tau. This is in contrast to counterfactual quantities, where here, if we were interested in the outcome under treatment at time tau, but we're in the control group, this is something that we can't identify with consistency. We need more assumptions for identifying this, because this is a counterfactual quantity. We don't directly observe this. And then same for this other one here. So if we were interested in the potential outcome under no treatment, if we are not in the control group, we're in the treatment group, then that's a counterfactual quantity. Consistency doesn't tell us anything about that. Okay, so that was just extending the consistency assumption. And now we're going to see what's probably the defining assumption for difference and differences, the parallel trends assumption. So we were interested in identifying this ATT quantity here, but we needed some assumptions to identify that. And the main thing that we noted is that we observe these two blue points, so we can get the difference between them. And we observe this bottom red point, so we can add this difference onto this bottom red point to get what we hope to be this counterfactual quantity that we've denoted by this gray point. Okay, so the parallel trends assumption is that these two vertical distances between the two blue points and between the red and the gray point are the same. These two blue intervals are of the same length. An equivalent way of saying that is that this black line connecting the two blue points and the dotted gray line connecting the red and the gray point are the same slope. In other words, they're parallel lines. That's why it's called the parallel trends assumption. Okay, so we're saying that we can get this counterfactual quantity from this observed quantity and these two observed quantities by assuming that when we increase from this quantity where we don't have treatment to a quantity that we still don't have treatment but now some time has passed, we're assuming that the increase would be the same as it was in the control group, where we also didn't have treatment. That's the kind of graphical picture to have in mind, and then writing down the parallel trends assumption mathematically looks like this. So on the left-hand side here, this term exactly matches this term, and we're saying minus, so that's this vertical distance, this term, where this term equals this term because of something that we'll see on the next slide. And these two terms equal this term and this term because of just consistency. So we're in the control group y0 and y0. So we can just throw in the 0 potential outcome there. Okay, but why is this term equal to this one right here? Right, so this has the potential outcome 0, which doesn't match the treatment. Treatment equals 1. So we can't just use consistency to get from this guy to this guy. So that's what we'll see now with the no pretreatment effect assumption. And we'll just go ahead and write this right away on the bottom here. We have the no pretreatment effect assumption tells us that these two quantities are equal. So what are the two quantities here? One on the right-hand side is this one, which we saw on the previous slide. And then this one is equal to this quantity, which we observed by consistency, because t equals 1, so we can just throw in the potential outcome 1 there. And then this is one we want to know on the previous slide. We'll see a more clear use of this assumption in the proof that's coming up shortly. And it might seem obvious, like this assumption should always be satisfied. So what is this assumption saying? It's saying that there's no treatment effect here in the treatment group before the treatment's been administered, that there's no treatment effect there. It's like, well, of course, the treatment hasn't been administered. So why would there be a treatment effect? But there are cases where this assumption is violated. So for example, if people are anticipating the treatment that they'll be getting soon, then they might act a bit differently than if they weren't anticipating that they would get that treatment. So the treatment does have some effect on them. So this is something to make sure is actually satisfied. This assumption is actually satisfied if you're using difference in differences in practice. All right, so before we get to the proof, let's kind of take stock and compare the assumptions we have now to ones that we've seen throughout this course. So I'll put the causal estimand we're interested in on the left and the assumption on the right, the assumption that helps us identify that causal estimand. The thing that we saw initially was the average treatment effect on the treated when we didn't have any time. Okay, so this is the ATE. If you didn't condition on t equals 1 here, that's just the ATE, and that's the thing that we've been interested in all throughout this course. I just have the ATT here, so it's going to be a bit more comparable to the estimand that we see that it does involve time now. So the assumption that's important for identifying this causal estimand is this unconfoundedness assumption, where y0 is independent of treatment. And we're going to contrast that with the assumption that we use for difference in differences. So here is the quantity we care about for difference in differences. It's the same as the above one, but now, because time is involved, we have to specify that we're specifically interested in time 1, right? So that's after treatment has happened. And the defining assumption here is the parallel trends assumption. So this assumption is saying that this difference of the potential outcomes under no treatment, where the difference is between the potential outcome under no treatment at time 1 and under no treatment at time 0, this difference is equal in both the treated group and the control group. That's the parallel trends assumption. So because it's in both treatment groups, it doesn't matter which treatment group you're in, you could think of this as an independence assumption, where instead of it being this single potential outcome y0 that's independent of t, and now it's actually this difference that we're assuming is independent of t, this difference across time. So it's still y0 in both cases, but the first one is y0 at time 1 after treatment has been administered, and the second one is y0 at time 0 before treatment was administered. So parallel trends is kind of like this unconfoundedness in difference space assumption. And we could have specified it as mean independence, right? So this is mean independence here, and then this is full independence. So it's a bit stronger of an assumption, but it's just a bit easier to look at this independence and this independence than mean independence ones. And with all those assumptions out of the way, we can get to the proof. So recall that difference in differences, what we're interested in showing is that this quantity, the ATT, is equal to the difference between this difference and this difference, where the graphical intuition for this first two terms is this whole red vertical, and then the blue is this blue vertical, which by the parallel trends is we get from this blue vertical. And then we're taking the difference between this red and this blue to get this purple. So that's what this equation you can think of is going on in this equation graphically. And now we're going to prove this equation using these assumptions that we just covered. All right, so here's that equation with the causal estimand on the top left and the statistical estimand on the bottom right. As usual, the first thing we do is apply linearity of expectation. Then we can immediately identify this first term on the right-hand side using the consistency assumption. So basically, what we need to do to identify this ATT causal estimand is to identify this specific counterfactual causal estimand here. So if you look at the common trends assumption, that term shows up right here. So this guy is this guy. So if we just solve for this guy, then we get this. And the last two terms here are terms that we can just reduce using consistency to these statistical estimands here, just these conditional expectations. Now, unfortunately, we still have a counterfactual term here, this guy. So it's different from this guy, and that now we're at now we're at time 0 rather than at time 1 like we were here. Okay, so how do we identify this guy? And that's where the no pretreatment effect assumption comes into play. So this term shows up exactly here. The no pretreatment effect assumption tells us that this term equals this term. So we can just substitute in that term. And now we finally have a term that we can identify. So here, the potential outcome 1 matches the treatment group 1. So we can just use the consistency assumption to turn that into this conditional expectation with no potential outcomes involved. And that's it. Now all that remains, now that we've removed potential outcomes from this term, is just plug this term back in up here, and that gives us this. Then just by regrouping terms, we get this more familiar difference in differences. So this is the difference in differences, are these two, equation. That completes the proof. All right, so this slide is a bunch of equations and stuff, but what about the graphical intuition? That's the next question. What is the graphical intuition behind the various parts of the proof and assumptions on the previous slide?